Let's consider the idea of a subset now. The idea behind a subset is we take a set and if we consider its elements, and if all of those elements in one set are also contained in another set, well then we would say that one set is a subset of the other set. So for example, if we have a set A and A has 5 elements, for example 1, 2, 3, 4, 5, the numbers 1, 2, 3, 4, 5, and if we have a set B and B contains the elements 1, 2, 3, 4, 5 and 6, well then every element that is in A is also in B. In this case we would say that the set A is a subset of the set B. So the criteria that we're checking here is that for every element in set A, if that element is also in the set B, then A is a subset of B. Okay, the symbolism we use to write this is this symbol here. This is read as A is a subset of B. Or alternatively, if we want to switch the direction of the symbol, this here is read also A is a subset of B, or B contains the set A. The symbol, the two dashes with the arrow, this is read as implies. So if we were to take this statement here, we would read it, A is an element of A implies that A is an element of B. And what we're trying to get across here is the idea that if A is an element of the set A, then it is also an element of the set B. Okay, so more formally, we can look at a definition of what a subset is. So, given the set A is a subset of the set B, written A subset B, if every element in A is also an element of B. This means that for every X, if X is an element of A, then X is an element of B. So it's important here to note that every element that is in A has to be in B. There can be no exceptions. So for example, if we let A be the set of numbers 1, 2, 3, 4 and 5, and if B is the set of numbers 4, 3 and 1, then B is a subset of A is true. And the reason this is true is, if we look at each of the elements of B, starting with the number 4, we can check to see if that element is also in A. So the number 4 is in B, and it's also in A. The number 3 is in B, and it also is in A too. The number 1 is an element of B, and the number 1 is also an element of A. So in this case, we can see that B is a subset of A. Okay, if we switch this around and consider, is A a subset of B? The answer in this case would be no. Okay, to see that, let's have a look at some of the elements of A and see if they're also in B. So just by inspection, we can see that 2 is an element of A. Let's check to see if 2 is in B. It isn't. So in this case, A is not a subset of B. Now, the notion of a subset can also be used to consider whether two sets are equal to each other. Now, two sets are equal if they both have exactly the same elements. So another way of thinking about this is by seeing that two sets are equal if each is contained in the other. And what we mean by this then, if we were given two sets A and B, if A is a subset of B and B is also a subset of A, well then this idea of equality holds between them. In that case, we could say that A equals B. They're the same set. They both have the same set of elements. So let's look at an example again. So in this case, we have the set A with elements 1, 2, 3, 4 and 5, and the set B with elements 4, 3, 1, 2 and 5. Okay, the order of the elements here is changed, but we know that the order of the elements doesn't matter when we're actually considering sets. So for each of the elements in A, if we can find that element in B, we'll know that A is a subset of B. So just by inspection, we can see 1 is an element of A and 1 is also an element of B. 2 is an element of A, 2 is also an element of B. 3 is an element of A, 3 is also an element of B. 4 is an element of A, 4 is also an element of B. And finally 5 is an element of A, and 5 is also an element of B. So that implies that A is a subset of B. Okay, So let's see if it works the other way around then. Let's look at the elements of B and see if they're contained in the set A. So the first element listed here is 4. So 4 is an element of B. Let's check if 4 is also in A, and it is. Next one, 3 is an element of B. 3 is also an element of A. 1 is an element of B. 1 is also an element of A. 2 is an element of B. 2 is also an element of A. And finally, 5 is an element of B. 5 is also an element of A. So we can see that B is also a subset of A. So the results of that are A is a subset of B and B is a subset of A. So A is contained in B and B is also contained in A. In this case, we can see that they are equal. So as a definition of set equality, we can take the following. A is equal to B, the set A is equal to the set B, written as A equals B, means that A and B have exactly the same elements. So this would mean that A is a subset of B and B is a subset of A. And we know from the previous example that we had a few slides back that this isn't always the case. Just because A is a subset of B doesn't necessarily mean that B is a subset of A. But if it does hold true, then we can say that the sets are equal. Okay, so the example we had here, is A a subset of B? Yes. And is B a subset of A? Yes. Therefore, this implies that A equals B. Now, two sets that we commonly encounter when we're dealing with problems in set theory are the empty set and the universal set. And we've made reference to this earlier on also, that a set can contain no elements, in which case we call it the empty set or the null set, and we denote the empty set by an open curly brace followed by a closing curly brace with no elements listed between the braces. Or else we use this 0 with a dash through it to represent the null set. Okay, the universal set is somewhat of a misnomer. We are not considering every possible thing in the universe as part of the universal set. When we consider a universal set, we're really looking at the domain of the problem at hand and the actual elements contained in a larger set, the set of interest for a particular problem. So all sets under investigation in any application of set theory are assumed to be contained in some large fixed set called this universal set, or also sometimes it might be called the universe of discourse. So for example, we could consider the set of all students at NCI as the universal set. And then as a subset of that universal set, we could consider the set of all students in Introduction to Mathematics for Computing. Okay, so depending on the problem at hand, the universal set will change. So we have this idea of a null set, an empty set containing nothing, and also for a given problem we have the universal set, the set containing all of the elements that we're interested in for a particular problem. Typically the universal set is denoted by an uppercase U. Okay. We also looked earlier on at the idea of cardinality, and the idea of cardinality has to do with how many elements are in an actual set. Let's take a definition. A set A is called finite if it has n distinct elements where n is some natural number. So what this means is that we can actually count all of the elements in the set, and we'll actually reach a point where we've exhausted all of the elements in the set. So n is called the cardinality of the set and is denoted by the set name with 2 bars surrounding it. So as an example, if we have the set A with the elements 1, 2, 5, 6 and 9, what we need to do is actually count how many elements are in that set, and we can see that we've got 5 elements in the set, so the cardinality of this set in the example is 5. Now in some cases we will encounter sets with an infinite number of elements, and we will also have to entertain the thought that some sets have a countably infinite set of elements, and other sets will be uncountably infinite in terms of the number of elements they have. And really what that means is that if we can actually form an association with the elements of a set and put them into one-to-one correspondence with the natural numbers, we would then say that it is countably infinite. So for example, the natural numbers themselves are countably infinite because we can form the association of each number in the set n, the natural numbers, with itself. We will also see that the set of rational numbers is countably infinite. So in terms of the natural numbers and the rational numbers, their infinities are the same type of infinity. Even though intuitively we may feel that there's more rational numbers than natural numbers, it turns out that in terms of infinity, they're both countably infinite. So all of the rational numbers can actually be enumerated, put in one-to-one correspondence with the natural numbers. When it comes to the real numbers, however, we cannot form that one-to-one association with the natural numbers. So the set of real numbers, and recall the real numbers are both the rational numbers and the irrational numbers, that would be a set that would be deemed uncountably infinite. So as a supplemental information sheet, we will do some more work on proving that the set of rational numbers is countable and that the set of irrational numbers is uncountable. Let's take a look at this idea of subsets in a bit more detail. So we'll take an example. Okay, let's consider two sets. The first set we'll call A, and we'll define this using set builder notation as the set X, such that X is an element of the real numbers, and X is strictly greater than 2 and strictly less than 4. And let's consider a second set, B. Again, we'll define this using set builder notation as the set of all X, such that, again, X is a real number, and this time X is strictly greater than 1 and strictly less than 5. So we have two questions we need to answer. The first question is A a subset of B? And secondly, is B a subset of A? Okay, so the idea with a subset is, if we're given a set, we need to check if all of the elements in that set are also contained in another set. In that case, we would say that the set we're looking at is a subset of the other set. So for the set A, let's have a look at all of the elements in the set A. So let's take a sample of an element from the set A, and we'll call it lowercase a. So let A be an element from the set A. So what can we say about this element A? Well, looking at the definition, we know that A has to be greater than 2 and it has to be less than 4. Okay, so we'll break this up into two separate parts. So let me just write those down. We have A is greater than 2, and secondly, we have that A is less than 4. Now, if A is greater than 2, what can we say about that? Well, we can also say that A is greater than 1. And if A is less than 4, what else can we say about A? Well, we can say that A is definitely less than 5 in this case as well. So for all elements A in the set A, we have that A is greater than 1 and A is also less than 5. So let's have a look at the definition of the set B then. B contains all elements X, such that X is a real number, X is greater than 1, and X is less than 5. So for any element we choose from A would also be an element of the set B. So in this case we can see that the set A is a subset of the set B.